Stefan, kannst du mich hören? Gut. Ich weiß leider immer noch nicht, wie ich dich jetzt hier zum Host mache. Let's go to Analogue. Ja. Aber okay, da, ja. Make Host. Yes. Jetzt bist du der Host. Ist das okay?
Ja, okay, aber Co-Host machen.
Ach so. Das musst du dann jetzt wahrscheinlich tun. Stimmt, ja. So, dann mache ich dich. Wo ist denn? Ich sehe hier nur Make Host, kein Make Co-Host. Na gut, mal schauen, dass wir das hier starten. Okay. Sieht man die? Achso. Ups. Ja, ich versuche das gerade. Share. Das da. Share. Seht ihr jetzt die Folien? Okay, jetzt muss ich sie irgendwie noch hier auf den Beamer bringen. Okay. Sieht man sie immer noch? Okay, gut. Okay. Weißt du, ob der Stream jetzt auch funktioniert? Ob der Stream funktioniert? Ich weiß jetzt nicht, wer auf dem Stream zuhört. Okay, can you hear me over the microphone? No. Can you hear me now? The microphone? Or just directly? Stefan, weißt du, ob der Ton über den Stream funktioniert? Scheiße. Nein, der Stream-Ton müsste ja über das andere Mikrofon kommen. Ah, ja, okay. Hört man das jetzt? you hear me now? Does this work? I think it should work, huh? Okay. All right. Sorry, we're a few minutes late, so let's get started. This is a bit of a hack here. I hope everybody can hear me. If the stream doesn't work, please try to switch to Zoom. So last week we talked about diodes. We saw a number of circuits with diodes where we treated the diode as an ideal device that simply conducts in one direction and does not conduct in the other. And now we want to switch to looking at real diodes, which are today most of the time semiconductor diodes. So we started by looking at properties of semiconductors, and the most relevant here are the fact that there are movable charges, mobile charge carriers, electrons negatively charged, and holes that are positively charged that can be treated as mobile charge carriers. And we can increase or decrease the number of charge carriers by adding so-called donors and acceptors. So for instance, as you see here, when we add donors to a semiconductor, we increase the number of mobile electrons, which on the other hand then decreases the number of holes in the same region because we have more recombination. So in a region that is doped with donors, then the number of electrons is much higher than the number of holes. And therefore, the electrons in this region are called the majority carriers, while the holes in the same region will be called minority carriers. The same thing can be done in the other direction. So if we add acceptors to a region, then we increase the hole density, denoted by P because they're positively charged, and we decrease at the same time the electron density, which is denoted by N for negatively charged. So now we have P much greater than N, and therefore the holes are now called the majority carriers and the electrons are called the minority carriers. In equilibrium, the product of hole density and electron density remains constant, and the product is called the square of the intrinsic charge density, because when we're in an intrinsic semiconductor, P and N are equal, so this is just the square of the intrinsic density. But the product still is constant when we're not intrinsic, but we have doped the semiconductor. So this is graphically shown here. You see on the horizontal axis the number density in per cubic centimeter. So the intrinsic carrier density is something like 10 to the 10. The number of atoms is something like 10 to the 22. And the doping densities that are of interest for technological reasons are of the order of 10 to the 15 to 10 to the 18. So that gives us majority carrier densities that are much higher than the intrinsic density, but still also a lot smaller than the total number of atoms. And at the same time, the minority carrier density is reduced by several orders of magnitude and is now down to 10 to the 3, for instance. Okay. The last important effect that we need to understand, that we need for understanding semiconductor devices, is charge transport. So there are two important effects here. One is drift, which is similar to what happens in a conductor. So the charges are moved by an electric field. The difference with respect to a conductor is that the charge carrier densities are typically much smaller. So in a metal, we have basically the same number of free electrons as we have atoms, while here we have several orders of magnitude less. And the other relevant difference is that now we have two types of charge carriers. So in a metal, we basically only need to worry about electrons, but now we have electrons and holes. So the total drift current is the sum of the drift current caused by electrons and by holes. So this is This is shown here. The electrons shown in red when the electric field points to the right. The electrons are negatively charged and will be moved to the left, and the holes will be moved to the right. So this arrow denotes the average velocity, so to speak, while the current has the same direction for both, because the direction is different, but the charge is opposite as well. So the net current direction is the same for both types of charge. The second important feature is diffusion, which tends to equalize density in a volume by random motion. So for an individual electron or hole, this is just a random walk through the material. But if you look at the total ensemble, this tends to lead to a particle current that is opposite to the density gradient. So, and the constant of proportionality is called the diffusion coefficient. So this also contributes to the electric current, and this contribution can be large actually. It can even be stronger than drift in some cases, and the direction depends on the charge carrier sign again. So it enters the total current with opposite signs here because the charge of the electrons is opposite to that of the charge of the holes. Here by Q I denote the absolute value of the charge of an electron. So the relevant coefficients, the mobility and the diffusion coefficients are actually not independent. So I mean this seems plausible because they're both sort of related to the mean free path in the volume. And the relation between the two is called the Einstein equation. So the diffusion coefficient is proportional to the mobility and multiplied by the Boltzmann constant and the temperature divided by the charge. This is called the Einstein equation because he was the first one to discover it. What is important to know is that electrons and holes have very different mobilities. So the mobility of electrons is roughly 3 times larger than the mobility of holes in silicon. So when you have a certain field and you have an electron and a hole, then the velocity, the current related to the electrons, when you have the same density, will be 3 times higher than the current that is connected to the holes. So the table here shows the mobility values for a few semiconductors, and you can see that silicon does not have the highest mobility. There are other materials that have higher mobilities, and this usually gives then rise to faster devices, for instance. But the silicon technology is usually much better under control. So most devices use silicon, and only in some more, let's say, more demanding applications, people resort to other materials that offer higher mobilities. Okay. This concludes our little excursion into semiconductor physics, and now we start looking at p-n junctions. So a p-n junction is a contact region between a p-doped and an n-doped volume. It can look like here on top, and this is the type of junction that we'll discuss in the next slides. So just a rectangular interface. In practice, they usually look different. When they're produced in a planar technology, for instance, then you have like a p region that is embedded in a larger disk of n material or something similar. But the relevant features are the same. The relevant is what happens at the interface between the p-doped and the n-doped value. So, and these p-n junctions are, of course, the key ingredient to all semiconductor devices. Today we'll only talk about diodes, but next week we'll see that they also are the key feature in bipolar junction transistors, field effect transistors, and some others. Okay, let's start with a bit of a cartoon. What happens when you bring a p region and an n region together? So we make a thought experiment. So we first have them separate. So on the left-hand side, we have a p region, and next to it, a piece of intrinsic silicon. So in the p region, you have these circles that depict the ionized acceptor, and the blue volume, which is the the sea of the mobile holes. On the other hand, you have in the end silicon the ionized donors, which are positively charged, and they're embedded in the mobile electrons. And the whole thing is, of course, neutral because you have the same number of ionized donors and ionized electrons. Now, if you have a region, a situation like this, where the electrons on the right-hand side or the holes on the left-hand side can actually freely move around, then it's clear that it will not stay like this, but they will diffuse. The holes will diffuse into the region where there are no holes, because there's a huge density gradient, and the same on this side. So the electrons will diffuse into the region where there are no electrons. So we end up in a situation like this, where we have a net positive charge, for instance, in this region from the holes that moved here, and we have a net negative charge from the donors, from the acceptors that stay here, and the opposite thing happens on the other side. This diffusion then will eventually stop because this field grows larger and larger, and at some point we have an equilibrium between electric field, which causes a drift current, and the diffusion current into the region of lower density. At that point, we can then, as a thought experiment again, bring the two together. So we make we put the N region here and the P and we get this. So now we have again a volume of holes, for instance, on this side, which have to some extent diffused into the other side, and electrons here, which have diffused to the left-hand side. And there's an electric field in between. So in the middle now we have a region that has electrons and holes. But at that point, then recombination kicks in and reduces the number of both types of carriers. So because of the mass action law, again, we can say that the product of the two will be Ni squared, so very, very small. For instance, if you now consider the region, just the middle of two symmetric regions of P and N silicon, then from symmetry you can argue that at the interface exactly the two numbers will be equal, and hence both of them will be the intrinsic number density. So this means that in the middle here, the P and the N densities will be much, much smaller than the acceptor and donor numbers that we have left and right. So this is therefore a region now that is almost completely depleted of charge carriers, and is hence called the depletion zone, which develops when we bring a P region and an N region together. In this region, of course, the ionized dopants are still there. They cannot move around. We have a space charge in this region. So while this region and this region are electrically neutral, here we have a space charge because the donors and acceptors are still there, but all the mobile carriers have disappeared. This is often also shown in terms of a energy band diagram. So here we have the P region with the acceptors, when it's ionized, we have holes here. And to have holes, more holes here and less electrons there, this corresponds to moving the Fermi level down from the middle. And on the other side, we have the donor and the electron. Having more electrons in the conduction band means that the Fermi level must be closer to the conduction band. So here we have a difference in Fermi level. And if we bring the two together, they form one common thermodynamic system. So the Fermi level must be the same left and right. And the only way to do this is, of course, to change the value of the conduction bands and the valence band. So we have in this region a bending of the energy bands, and this corresponds to the electric field that we have, and it forms a potential barrier for the charge carriers. Okay, so this is just a summary. I think we can go on now. We will start with a numerical example of a PN junction. So we have a p-doped volume on the left-hand side with 2 times 10 to the 16 acceptors per cubic centimeter, and on the other side we have 10 to the 16, so half the density of donors. we'll make some simplification. So we treat this as one-dimensional thing and stationary, but still, if you take all the effects into account, you cannot get a full analytic solution of this. So we'll just show you the result of a numerical solution, and we'll later look at some approximations. So this is what happens for the potential and the electric field. So the electric field here, the red curve, is 0 when you go far away from the junction, and it is non-zero when you're in the junction region. And it has this almost linear shape here, and this is of course because the charge density in this volume is constant. So when you have a constant charge density, that means that your field will grow linearly when you go across the volume. And then here you have the opposite charge and it will fall again. You will also see that the whole thing is somewhat asymmetric, so it extends further to the right-hand side and less to the left-hand side, and this is because we have an asymmetric doping. In technical devices, the doping is often a lot more asymmetric, and that will also lead to very asymmetric junctions. The other thing that's shown here is the electric potential, which is just the integral over the electric field. So here there's no field, the potential is constant, and then here the potential goes up and becomes constant again. And the difference between the left and right is called the built-in potential. And it's typically in silicon, in this case, it's 0.7 volts roughly for these numbers. It depends on the doping. We'll come back to that. Okay. In the same example, one can also find the charge carrier density, and that is shown here. You have in the depletion region, which is a fraction of a micrometer wide in this case, you have almost no mobile carriers. And then on the left-hand side, for instance, you have a high density of holes. So the holes is the density of holes is equal to the number of acceptors when you're far away from the junction, and the number of electrons is equal to the number of donors also when you're far away from this junction. And the number of minority carriers, which is the electrons in the p region and the holes in the n region, is basically invisible on a linear scale. Later we'll also look at this on a log scale, then you see there are some, but the number is much smaller than the number of majority carriers. So the net space charge is given by the sum of mobile carriers and the fixed ion and ionized dopants. So here we have no mobile charges, but we do have the dopants, and the effect of that is shown here. So here we multiplied each charge carrier density with its charge. So it's positive for the holes, negative for the electrons. So that's the same curve for the holes and the electrons. And then the number of acceptors, which are negative, is shown here. So it's minus 2 times 10 to the 16. And then the number of donors multiplied with their charge is here. So it's 10 to the 16 here. And the total charge density is then the sum of all that. And this is shown here. So the black curve is the resulting net charge density. So it's negative on the left-hand side, it's positive on the right-hand side. So the depletion region, for this reason, is also called the space charge region. So in the next steps, we'll make an approximation here. So this varying curve will be approximated by a simple box curve, where we say that there are no carriers inside the depletion region and the normal density outside the depletion region. This is called the depletion approximation, because we say there are absolutely no carriers inside the depletion region. And so these 2 points we'll call minus xp and plus xn. And then one can actually make a simple calculation here to find the field and the potential in this approximation. So this is the approximated charge density. So it's minus q times the number of acceptors and plus Q times number of donors here, and it's 0 outside. And from the neutrality of the whole thing, we know that, of course, the product of the two must be the same. So the total area on the curve must vanish, otherwise the whole device would be charged. Okay, the electric field is simply the integral over this, and as I already said, when you integrate over a constant charge, you will get a linearly rising electric field. Here you flip the sign of the charge density, so the sign of the change of the electric field changes again, so you get this triangular shape of the electric field. This is the expression. You have the dielectric constant in there as well, and the width of the regions. If you integrate again, you get the electrostatic potential. So you start with some constant value on the left, and then integrating over the linear function here gives you a quadratic function with factor 1/2 in front of it. And here you have to switch because you switch to the other sign, and you get this quadratic function with a minus sign, and again the same factor in front of it. But this time you have the number of donors, where before you had the number of acceptors. The two pieces must be continuous, of course, in the middle. Not unfortunately in the graph there, not quite. Oh yes, they are. So they have to be continuous in the middle. So when you put 0 in here for x, then the two terms must be the same. So this potential, the potential far away from the junction on the left-hand side, plus this constant, this expression times xp squared must be the potential on the far away from the junction on the n side, minus this constant here divided multiplied by xn squared. And so we take these two results and can then rearrange things a bit. So we have now, we write the difference of the two potentials, left and right, and this will be our built-in voltage. Then we have these two terms here, and but here we have xp and xn, and what we are going to do now is to replace one and or the other. So like I said, here this difference here is the built-in voltage. We multiply by this constant here, twice the dielectric constant divided by the charge. Then on the right-hand side, we only have the carrier densities, the acceptor densities, and the donor densities multiplied by this, the sizes of the depleted region squared. And now we can use this here and replace, for instance, xn by xp. So xn is equal to xp times this ratio. And then this becomes na plus na squared divided by nd multiplied by xp squared. So now we have a relation between xp and the built-in potential, and you can write this like this. So xp is the square root of this expression here, where you have the built-in potential and this combination of the carrier densities. Of course, you can also play this the other way around, and then you get the value of xn as a function of the built-in potential and the densities of acceptors and donors. So now we can, from this, we can read off the size of the depleted region as a function of the built-in voltage. This is just rewriting it to make clear that we have the same term here, the same denominator in the square root, because then we can just take the sum of the two, and the sum of the two is the total width of the depleted region, and it can simply be written like this. So we have here a factor that is proportional to this to the density of the dopants, and here we have an expression that is proportional to the square root of the built-in voltage. So we haven't determined the built-in voltage yet. We'll do that in the next couple of slides. But I can already say that the built-in voltage depends only very weakly on the doping. So we can sort of make a statement that this expression is typically only a few micrometers large. And if you look at this term here, it is, you can also say see that it is this function of acceptors and donors, so square root of 1 over donors plus 1 over 1 over the number of acceptors. So if you want a large depleted volumes, then you want small doping. And this is important when you want to have diodes that can operate with high voltages, because if the depleted volume is large, then you have relatively small electric fields. So if you make a small junction, then you get very high electric fields, and that will not work for high voltages. So high voltage diodes will have a low doping. The other reason why you want low doping is if you build, for instance, a particle detector, and this is what we do. We use diodes essentially as particle detectors, and we want large depleted volumes. And to do that, you need very low doping, at least on one side of the junction. That can actually be difficult to get this very low doping, because that requires getting very pure material. And in these applications, the size of the depleted region can be up to several hundred microns, while in a normal diode that you usually use, it will be a fraction of a micron or a few microns. On the other hand, if you make these dopings very, very high, you get very small depleted regions, less than a micron. And this is also exploited in some devices, in so-called Zener diodes or tunnel diodes, where you want this depleted volume to be very small, and it can be much less than or it can be smaller than a micron in these devices. The other thing that you can read off here is that the depleted volume is proportional to the square root of the built-in voltage, and we will later just use the fact that when you apply an external voltage or a so-called bias voltage, then this built-in voltage is replaced by the difference between the built-in voltage and this external voltage. So when you apply a positive voltage with this sign convention, then the width of the depleted region will shrink. If, on the other hand, you apply a negative voltage, then the width of this depleted region will grow. And this has consequences for these devices. Okay. Now we can look at the dynamics a bit more in this depletion approximation. So now we have the holes, the majority carriers on the left side, with a few minority electrons sprinkled in the volume, and the opposite situation in the N region. And we assume there are no carriers in between. So the majority densities are given by doping, and the minority carriers are much smaller, even than the intrinsic value, reduced by recombination according to the mass action law. So all these carriers can do random walks, so they just wander around, and it's clear that if some of them get into this electric field, they would just be swept away. So when such a carrier walks into the depleted region, then the minority carriers will be swept over to the other side, because the sign just matches. However, the majority carriers are repelled by the field. So if you're an electron, for instance, on this side, and the electric field goes here, then it has the wrong direction. So the electron will be pushed back, and while a hole that comes from here will be pulled over to the other side. Okay. So for the majority carriers, this is a potential barrier, and only a small fraction of these majority carriers can climb across this potential barrier. The equilibrium carrier densities we've seen in the last lecture can be derived from thermodynamics, and they're given by these exponential expressions here. So we have the e to the minus difference between the conduction band and the Fermi level for the electrons, and here we have the difference between the valence band and the Fermi level for the holes. We've seen before that the Fermi level is the same, left and right, and the value of these bands changes, and this goes in accordance with the change of the density of the carriers. So we know that for instance, for the electrons, when you look at electrons, the number of electrons at this point of the junction is given by this expression here, and the number of electrons on that side of the junction is given by the same expression, but using now the value of the conduction band at that point. So the first factor here cancels, and we're left with this exponential. So we have the difference of the electron energy of the conduction band energy at this point here, xp, and the conduction band energy at xn. So this is essentially the built-in voltage. So we know that the carrier density between the left-hand side and the right-hand side are related by this exponential factor, and this is quite universal. So the number density of electrons left and right of the junction is related by an exponential of the difference of the energy of the two, and the same holds for holes. You can write down the same thing for holes here. So there's the same exponential factor because we have the same difference also for the valence for the valence band. Okay, so this exponential behavior is very important. It's called sometimes called the law of the junction. So we just derived it for equilibrium using this expression, of course. But we will use it also when we are not too far from equilibrium. And the reason that this works is that the currents that are caused by external voltages are usually small compared to the currents to the internal drift and diffusion currents, so that this will still hold even if we go a little bit away from the equilibrium. So the exponent here was this term, the energy difference divided by the Boltzmann temperature divided by T, the temperature. And because we have charged particles, of course, then the energy difference is the charge multiplied by the voltage difference. And then we have this term, and this combination of numbers here, Q divided by K Boltzmann and T, or the inverse of that actually, is then again a voltage, and it's called the thermal voltage. If you put in the numbers for room temperature, this comes out to be roughly 26 millivolts. So the exponent will from now on most of the time be written as the voltage difference divided by the thermal voltage. Now at equilibrium, we know that the voltage difference across the potential is by definition the built-in voltage. We also know the majority carrier densities because it's the doping. We know the minority carrier density because we know the mass action law. So it is given by this expression. We will apply the junction law. So the density on the left-hand side is the minority density, is the majority density multiplied by this exponential factor. And from this we can calculate the built-in voltage, and then we get this expression. So it's the product of the thermal voltage multiplied by the logarithm of the doping, of this combination of doping concentrations. So this gives us the built-in voltage from the doping. And if you put in numbers for silicon at room temperature, it typically comes out between 0.6 and 0.9 volts. So in the example that we've seen at the beginning, it was 0.7 volts, for instance. But it's only a logarithmic function of the doping. So that's why it's typically always more or less in this region. Okay. This exponential drop of the density can be visualized nicely in an analogy. And if you think of vapor on top of a liquid, so we know that the density drops by this exponential function. So when you have this barrier, a barrier here, then the volume, the density in this volume here is suppressed by e to the minus height of this barrier divided by Vt compared to the density that you have at the bottom. So this is like the vapor above a liquid. So this liquid has a constant vapor pressure at the surface, which is the result of evaporation and condensation. or the equivalent, of course, would be here the balance of recombination and generation for the charges. And the density as you go up decreases according to this parametric formula because of the gravitational field. So as you go away from this, the density of charge carriers goes down because the fraction of carriers that have enough energy to go so high just decreases exponentially. So we'll just use this analogy to look at what happens in such a junction now. Now we form the junction by bringing a second volume here where we have, let's say, a different liquid. So the vapor pressure here will be lower. If you have a barrier, then you can just do that. So the lower vapor pressure here, of course, corresponds to the reduced density due to the recombination with the majority electrons. So when you bring these two together and remove the barrier, you expect to see a net diffusion, of course, from the left to the right. So electrons, holes in this case, will move from the left to the right. So and you get a diffusion current that is proportional to the difference of densities left and right. So the lower plot here shows then the density as a function of this coordinate. So it's high on this side and low on that side. Now we know that the barrier reduces the density by this exponential factor, and we know that we are in equilibrium when we can bring the right-hand side up. So if we don't want this diffusion from the left to the right, we can simply lift up this to make sure that this volume is at the same level, at the level of the same density with the left-hand side volume, and this is done here. So here we have this exponential reduction with the height, and we bring this volume up to the point that we have equilibrium between the two. So now we can write that the density on the left-hand side, the whole density on the left-hand side multiplied by this exponential function is equal to the equilibrium whole density on the n side. And this is obviously fulfilled exactly when the junction potential is the built-in voltage. So this is how we define the built-in voltage. But now when we reduce the barrier height, so we are no longer at this level where we have equilibrium between the two. Now we reduce the barrier height, so this volume comes down. And now we clearly have an excess of carriers on this side. So there are more, there's higher density here than there. So you can see the graph here. So there's still an exponential drop across the barrier. But when we come to the other side of the barrier, we see there's too much compared to what we want to have in equilibrium on the other side. So the pressure difference, so to speak, between the two is given by this P0 on the P side multiplied by e to the minus built-in voltage minus external voltage divided by the thermal voltage. And then on the right-hand side, we have the equilibrium density of holes in the N volume. We rewrite that a little bit, and now we have, so we can split this exponential into two terms. So instead of e to the minus v built-in minus v voltage, now we have e to the minus v built-in times e to the minus voltage. And this factor here is now, when you look back to the previous slide, exactly the same as this term here because it's the equilibrium condition, okay? So we will replace this part of the exponential by the equilibrium density, and this leaves us with this term here. So the pressure difference is proportional to the density carrier on the n side multiplied by this term here, which is the e to the voltage. So there's no minus here, sorry, the exponential of voltage divided by the thermal voltage minus 1. And so what happens dynamically is that this will, of course, lead to diffusion. So we have too many holes here because there's an imbalance of the pressure. So the holes will diffuse into the N region. And in principle, this could continue until the N region is full. This will, of course, not happen because far away from the junction will still need to get to the equilibrium value. And the way that this happens is that there is increased recombination, of course. So the holes that are injected here into the N region will start recombination with the majority electrons in this region. So as you go away from the junction, the density will then slowly decrease and reach the equilibrium value. And it's this recombination that keeps the diffusion going. So it's not a static case, but this leads to a steady flow of charges from the P region into the N region. And this current is proportional to the density difference, so which is this term here. And this is called minority carrier injection. So the majority carriers on this side are injected to the other side where they become minority carriers. And this process is called minority carrier injection. And in diodes, this has an important effect because that is called diffusion capacitance, but it's also the key to the transistor action and in principle to the functioning of the diode itself. Okay. Now we go in the other direction. So go away from the equilibrium in the other direction. So we lift this one up, and now we increase the barrier height, and we still have the same expression for the density balance, but now we have the higher density here, which means that there will be an excess of holes trying to flow from the N-type into the P-type silicon. The expression is the same, and we get the same formula for the density imbalance and hence for the current. So the holes that come from here to there are then basically just drops in the ocean, so there's no injection here. This is not called injection. So they get into the field and drift into the P region. So we get a little bit of a depletion of holes here. So when this is the normal equilibrium, then the holes that are close to the junction will be swept away, which leads to a small depletion here of the minority carriers. And here we are, of course, everywhere have the normal expected density of the majority carriers. The current is proportional to this density imbalance, and if you make the voltage large enough, it becomes really independent of how high the barrier is, because it only depends on how many charge carriers you have here, and it doesn't really matter so much anymore how many are here if you just make it small enough. Okay, so the current in this direction becomes constant at some point, and you can see this here in the exponential. This term, when you have a negative voltage, then this term goes to 0, and you're only left with this -1 term. So the current becomes constant for very high negative values of the external voltage. Okay, let's summarize this, and then we take a short break. So the built-in voltage at the junction balances drift and diffusion. When we apply an external voltage, it modifies this barrier, and there will be a net current flow. All the currents in forward and backward direction have the same voltage dependence, so it's e to the voltage divided by the thermal voltage -1 for these two components, the injection and the drift. And we get the same expression for forward and reverse bias, forward being a positive voltage and reverse bias being a negative voltage. And we get the same expression for electrons and holes. So in so-called forward bias, the barrier height is reduced, while in reverse bias, the barrier height is increased. The depletion region shrinks. And if you take the depletion approximation seriously, it actually goes to 0 when the external voltage is equal to the built-in voltage. That doesn't really happen. That just means that at that point our model or approximation becomes invalid. But it is true that the depletion region shrinks in forward bias, while it grows when you apply a reverse bias. Here the in forward bias, the current grows exponentially, while here this term becomes negligible at some point, and the current becomes constant or very, very small and very, very small. In forward, we talk about minority carrier injection, so it's majority carriers that are injected and become minority carriers on the other side. And on the other hand, in the reverse bias, we have no charge injection. Okay, so I think we will take a break now and continue with the diode IV curve, which is of course exactly this term that we've just derived for the junction. Okay, so we'll be back, let's say, at 2:45. So Stefan, was this okay over Zoom?
Yeah, I guess the audio quality would be better over stream.
Okay.
I think it's the microphone, it's sometimes over amplifying, but
Ah,
the voice is right, I would say.
okay.
I think it's okay.
Good.
On my end, it sounds good.
Okay. All right. So see you later then. Okay, so let's continue. So now we'll look at the circuits with diodes, with junction diodes. The symbol of the diode is the same. So we have this triangle with a bar, and where this line is the N side, and on the flat side of the triangle we have the P side. So when the voltage applied in this way is positive, we are in forward bias, so the P side is more positive than the N side. And when the voltage applied in this scheme is negative, then we have the negative voltage on the P side, the positive voltage on the N side. That is called reverse bias. The IV curve of a real PN diode is given by this expression, which is the same as we had before. So this reflects the density, the densities of the charge carriers left and right of the junction. But for real diodes, there's a small correction factor here, which is called the ideality factor, which is typically between 1 and 3 for silicon. And the origin of this is the fact that we have completely neglected what happens inside the junction. So we just said we have this ideal exponential behavior between them, but really there are some effects like recombination when the particles cross the junction, and this modifies this a little bit, but the basic shape is still correct, and this is called the Shockley equation. The thermal voltage appears here, which is 25.9 millivolts at room temperature, and the factor in front of this depends on the geometry of the device, the size of the device, the doping of the device, and it's called the saturation current. It is very temperature dependent, and it contains, for instance, the intrinsic charge carrier density, because it's if you look at this, for here you have the carrier density at the junction in front of this, and this contains, for instance, the intrinsic charge carrier densities. That's why we have this term here, which is the gap energy. So it has this exponential dependence of the temperature through this term, but there's also another factor here from the diffusion and mobility constants. So there's a very strong temperature dependence on this saturation current. So the net effect is that even though you may think that the current goes down when you increase the temperature, when you look at this, that's not true. The net current actually grows when you increase the temperature for fixed voltage. But the voltage dependence is obviously what it is. So you have this steep exponential rise for positive voltages, and it becomes constant for negative voltages. So then only the -1 term here shows up, and this tends to become minus IS. That's why it's called the saturation current. So let's focus on the forward characteristic first. So whenever your applied voltage is larger than these 26 millivolts, you can neglect the constant term, and you have this pure exponential behavior. And this is actually valid for several orders of magnitudes for these diodes. So the diode behavior is pretty ideal. Not perfectly ideal, but pretty ideal. What's interesting is that there is no explicit threshold here. So we've seen that we treated these diodes as if there was a constant voltage above which they conducted, and there was no conductance below that voltage. But if you look at the Shockley formula, there's no such threshold in there. And in particular, there's no built-in voltage or anything like that. So the built-in voltage disappears from the Shockley formula. And the threshold behavior that we've always used is simply an effect of the steepness of the curve. So the operational range of a particular diode is typically a few orders of magnitude in current, so from a few milliamps to a few amps. And this leads then through the steepness of the curve to small voltages. So, sorry. So if you look at this and you change the current over a certain, you change the current over a wide range, you see that the change of voltage is relatively small. Okay, So this voltage change then is often negligible, and that makes it valid to treat it as if there was um, uh, as if there was a threshold voltage, but there really isn't any. There's no universal definition of this diode voltage. Some people define it as the diode voltage as being the voltage that you have when you apply 1/10 of the maximal applied current. This is completely arbitrary, but still a useful value. So here, when you look at a curve like this, you can say, okay, it's roughly 0.6 volts or roughly 0.7 volts for other diodes, and this would be your diode voltage. But this is just a very crude approximation. There is no actual threshold in there. So let's look at a real diode that is simulated here. You see the applied voltage on this axis and the resulting current here, and you see again this very steep increase of the curve, the exponential increase of the curve. And yes, I mean graphically this makes clear why people talk about a threshold here. We can, for instance, connect this with a resistor to some supply voltage here. Let's say a 1K ohm resistor. Then the current that flows through the diode is given by the difference of the output voltage and the supply voltage divided by the value of this resistor. So this current flows down here. So the same current through the resistor, of course, flows through the diode if there's no current going out here. This curve here can be shown as a straight line. So this is the current as a function of the output voltage, and this is of course the equation of a straight line. So it starts at V0 divided by R and then goes down to 0 here. If you want to know what the output voltage is, we can sort of make a graphical solution of this. Because actually the analytic solution of this is not possible. This is an equation that we cannot really solve analytically. But we can let Spice do it, or we do it graphically, and here we do it graphically for illustration. So the point where the two lines intersect is where the output voltage will really be. And in this case, when you have 5 volt output, 5 volt supply voltage, you end up with an output voltage of 733.6 millivolts. If now instead we change this voltage, for instance, we go down to 4 volts, then you get this equation. So here we have 4 volts minus V out divided by R gives you the green line here, and the intersection now is at 723 millivolts. So it's only 10 millivolts. It has changed only 10 millivolts, although we have changed this one by a whole volt. So this is sometimes expressed in terms of a supply rejection ratio. So we look at how much does this voltage change as a function of the voltage change here, and so we have 10 millivolts divided by 1 volt, so it's 1%. A circuit like this could in principle sorry, be used as a voltage reference. Because a voltage reference is something that gives you a constant voltage regardless of what your supply voltage is. That is often needed in circuits, that you have when you have a varying supply voltage or a voltage that you don't know exactly what it is, but you want your circuit to work with a constant reference voltage, then you need a voltage reference. And this is a simple example of a voltage reference. However, it is not really used in this way most of the time because of the temperature dependence of this curve. So when you change the temperature by a few degrees, then you will be off by several millivolts here. But for many circuits, we can ignore these changes and simply assume that the voltage is constant, and this helps us to when you want to intuitively understand what a circuit does, you can often just say, okay, this is a constant voltage, and then you go from there. We can also look at the reverse bias IV curve in more detail. So the Shockley formula in the reverse direction becomes constant. So you would have a minus IS for increasing negative bias, but it would become constant. You have very small currents in the nanoamp region. however, a very temperature-dependent current. So this one changes about a factor 2 for every 10 degrees C. What is not described by the Shockley formula is another effect that happens when you go too high in this negative voltage. There will be a breakdown at some point. Here it's shown at 8 volts, but it can be much higher voltages. So this breakdown is simply when the field is too high, there'll be sort of a spark inside, and this can be a useful feature. So it doesn't necessarily destroy the diode. So there are in fact diodes that are made to survive these. The breakdown can be very useful, and diodes with a wide range of breakdown voltages are available. So from a few volts out to kilovolts even. So how does this happen? When we go back to this picture of a PN diode again in this depletion picture. So we have a strong electric field in the depletion region. So we go P doped here and N doped on the other side. We have a very high potential barrier, that makes the majority carrier current negligible. So the majority carriers cannot cross the barrier that is produced by this electric field, but the minority carriers that diffuse into this region, they can go across, and that gives you the reverse bias current. However, when this field is very strong, sorry, they can be accelerated so much that they knock out valence electrons on their way through the diode. So they get so much energy from the electric field that when they scatter on a valence electron, they release this electron, and then you have electron multiplication. This is the same that happens when you have an electric discharge in air, for instance. So when you have a high electric field in air, the charges that are released can knock out electrons from other atoms, and this multiplies, and you get this avalanche effect. So this is called an avalanche breakdown, and it can be used technically. So the breakdown voltage is controlled by doping and of course also by the device geometry. So if you use stronger doping, then you get a thinner depletion region, you have higher fields, and then you have an earlier breakdown. And then the other direction, if you want a later breakdown, you need lower doping. That gives you a wider depletion region, then you have lower fields. So you need to apply higher voltages before you get the critical field that causes this avalanche breakdown. If you go to extremely thin depletion regions, so through very strong doping, then there's another effect that comes into play here. That's the so-called Zener breakdown. Then if you look at the band diagram of such a Zener diode, you can see that it's possible for a valence electron from the p side to go energetically. It's possible to go directly into the conduction band on the n side with enough reverse voltage applied. And when the depletion region is thin enough, then you can have a quantum mechanical tunneling effect, and this leads to a sizable current. So the breakdown voltage of these devices is typically less than 50 volts, and this is and they are called Zener diodes. Actually, both types, so the Zener diodes and the avalanche breakdown diodes are usually called Z or Zener diodes. And the symbol that is used for these diodes is like this or this. So it looks slightly different from the normal diode, although in principle they are normal diodes, but they're meant to be used in the breakdown mode. Let's see how this can be used. Typical applications are voltage regulation, transient suppression. So if you fear that on a voltage that you want to use, there are spikes on the voltage that you want to get rid of, or that you want to protect your circuit from, you can use these Zener diodes also from overvoltages. If you fear that supply voltage can be too high, that it would damage something, then the Zener voltage can protect your circuit, or it can also be used to protect humans, of course. If you want to make sure that a certain voltage at something that can be touched by a human being does not exceed a certain level. So two examples are shown here. Here you have, for instance, a floating supply that is connected over a long cable with some device far away. And then over this cable, you can have large voltage drops or voltage spikes, which can make this point go up to very high potentials, which would be problematic in some cases. And then you apply this interesting combination of Zener diodes, so they're basically facing each other. And this clips the voltage where this point can go to plus or minus the breakdown voltage. Right? So if you go beyond the breakdown voltage with this potential, then one or the depending on the sign, this one or this one will break down, and the other one is in forward direction anyway. So like this, you can limit or clip voltages at plus minus the breakdown voltage. Another example is a Zener is a voltage regulator based on a Zener diode, and we'll look at that here. So an example, you have an operating a load that operates at 5 volts, so it needs a 5 volt supply. It has a variable current consumption between, let's say, 0 and 100 milliamps. And you have a voltage source that can vary, for instance, between 7 and 9 volts. So this is an example for this would be a battery. When it's fresh, you have 9 volts, and when you use it for a time, the voltage drops, and you get down to 9 volts, but your device still wants 5 volts. So you can use the Zener diode to stabilize the voltage across the load to 5 volts. So you come in with the 7 or 9 volts here, or something in between. Then the Zener diode pulls it down to 5 volts because it becomes conducting when the voltage here is higher than that. But you also need a resistor to limit the current. Otherwise, you don't want the Zener diode connected directly to this supply, of course, because then you can have very large currents. So let's go through this example. The voltage drop across the resistor must allow the 100 millivolt current in your device, which is the maximum current, even at the lowest supply voltage. And if you design this, for example, for a lowest supply voltage of 7 volts, then the difference between the input voltage and the Zener voltage is only 2 volts. And so the current here is 2 volts divided by R, which must be at least 100 millivolts, 100 milliamps to supply your device. So this tells you that your resistor must be less than 20 ohms. So if you have a larger resistor than 20 ohms, then the voltage drop here will be too high, and this is not going to work anymore. So then, for instance, if you apply 7 volts at the input, and you have a load current of 100 milliamps, there will be no current flowing through the diode. Everything is just happy. So this picture shows the voltage across your load as a function of the input voltage. So here, for the case that you have no current, then of course the voltage will just follow up to a point linearly. So when there's no current, then there's no voltage drop. So this point just follows the input voltage, and here the Zener diode kicks in and stabilizes the voltage at 5 volts. If on the other hand you have 100 millivolts, then you have this voltage drop of 2 volts across this resistor. So below 2 volts, nothing happens. And then the output also starts following up to this point, so a little later. And then the output would rise above, at this point, would rise above 5 volts, but then again the Zener diode clips it, and it also stays here at 5 volts. So if then your input voltage goes to 9 volt, then the current that flows through the diode will be the difference between the current coming through the resistor. So it's input voltage, so 9 volt minus the Zener divided by R. So that's 4 volt divided by 20 ohm. And the load current we said is 100 milliamps. So the diode current at this point would be 100 milliamps. So you burn as much power in your diode as you burn in your device, and that's not very power efficient. So for high power applications, you will not do it. Sometimes people do it like this, but not when you use a lot of power. And this is too inefficient. And we will probably next week see ways around this that are much better using transistors. Okay, another feature of this curve, of the real diode IV curve, is the fact that it's nonlinear. Obviously, this is not a straight line, not an ohmic resistance. So the current as a function of voltage is not simply voltage divided by R, but when we are at a working point and have a small variation of a voltage, we can still argue that the variation of the resulting current is a linear function of the amplitude of the voltage change. Okay, so if you have a small delta U here, symbolized here by these sine waves, then we have a corresponding and proportional amplitude of the current that flows through the diode. So if you make it larger, then we get a larger response of the current here. And if we do this for not too large voltages, we can replace this section of the IV curve by a straight line, and then look at the so-called differential resistance. Right? So, and then delta U is R times delta I. So this is the first time we see this these differential resistance, and they will come back later to these when we do the small signal analysis of circuits. Now, if we change the working point, we get a different resistance. So that the slope of this curve becomes a function of the point where you are. So you get a different translation of input voltages to output currents depending on where you are. So now the application of this could be that you add a slowly varying signal to a fast varying sine wave. So you have this sine wave of constant amplitude, and you add a slowly varying signal here, and then what you get is at the output you get this fast varying sine wave, but with amplitudes that depend on where you are with your slowly varying signal voltage. And then this is a current. Usually you want a voltage, so you have to use, for instance, a resistor to translate this back to a voltage. This brings us to this nonlinear voltage divider here. So we have the diode and a resistor, and we clearly the voltage across both is the sum of the voltages across the resistor and the voltage across the diode. If you express this like you would for a voltage divider, so you want to know what is this point as a function of this voltage, but that's not so easy. You can only write it the other way around. So the voltage across both of them is the voltage of the resistor plus, and now here's the IV curve of the diode, where you replaced the inverse of the IV curve, where you replace the current by VR divided by R. This is graphically shown here. You have the current on the horizontal axis and the voltages on the vertical axis. So the ideal diode would look like this. So this is the logarithmic dependence, which is the inverted Shockley curve. And this is the linear curve of the resistor, and the sum of the two is shown here. So we are interested in the inversion of this. So we will just do this here by swapping the axis. So what we get here is now this curve. This is the response of this nonlinear voltage divider to an input voltage. You come in with an input voltage here, and this is the output voltage. This is the output voltage that you get of your nonlinear voltage divider. It's not the exact diode curve that we had before, but it's still nonlinear, and that's the only thing we need for this application. We need a nonlinear voltage divider. And a very simple application is shown here. So this is this nonlinear voltage divider. This is the IV curve of it that we've just discussed. And you apply now an input voltage that is the sum of a slowly varying triangle voltage, and on top of that you have the fast varying high frequency, or relatively high frequency sine wave. So and the result is shown here. So you have this triangular shape, and on top of that the fast sine wave. Now we take this. We've seen that the response depends on where you are. So if you now look at this voltage, we take it. We want to get rid of the offset that is applied and only want to look at how the amplitude changes. So we take this capacitor here and look at the voltage at this point. And then you get this result, which is a sine wave of the fast frequency that has an amplitude that varies with the voltage of the slowly varying signal that we applied. Okay, so here, for instance, we are at this point. So here the differential resistance of our diode or our voltage divider is very low. So it's very high, sorry. So we get a small response here. This is here. We remove the offset, so everything is around 0. And now, if we go to another point where we are working, for instance, in this region here, now the slope is highest, and we get the largest amplitude of the sine wave. So what we've done is we use the slow signal to set the working point between here and there, and then here we get a small response, and there we get a large response. So the nonlinearity of this device can be used to modulate the amplitude of a high frequency signal. And a circuit like this is called a mixer, because we effectively multiply the amplitude of the fast sine wave with the amplitude of the slowly varying signal here. These mixers are used then for modulating signals, for instance, in amplitude modulation radio worked like this. Okay, now let's come to another effect. So now we don't look at the IV curve, but a side effect of the fact that these are now real junction diodes. So junction diodes are like other diodes, usually used or very often used as rectifiers. So now if we have this circuit, for instance, we have a 5 ± 5 volts square wave, and we want to rectify it by sending it through through a very normal diode, and then with some load, a kilo ohm in this case. When this is an ideal diode, we would see this behavior. So the red one is the input voltage going from between plus or minus 5 volt here, and the output voltage at this node will follow the input voltage with a voltage drop of this diode voltage, 0.6 or 0.7 volt lower. But then when it comes negative, it cannot follow. It will stay at 0 and look like this. And then when it comes back again, we have the positive voltage again. So this is a rectified version of this. In the last lecture, we've seen this with sine waves, but of course it does the same thing when you have a square wave. Now, just as a thought experiment, we add a parallel capacitor to this diode now, and we will later see that this capacitor is in fact part of this diode. And when you're here, so you start out with 4.3 volts and this one, so we have 4.3 volts here and 5.5 volts here. So this capacitor is slightly charged by 0.7 volt in that direction. Then you, as a next, you switch the polarity of this supply here. So this point goes down, and the charge on the capacitor at that point is still there. So you still have the voltage of 0.7 volt across your capacitor, which means then when you go down here, the potential at this point will immediately follow, and then will go down to minus 5.7 volt in this case. Okay, so you have a sharp spike to minus 5.7 volts. But then the resistor starts pulling this point back to 0, and it does that with a time constant of R times C. So this R times this C, and it will slowly go back to this voltage. And at this point, it will of course also charge this capacitor to a much higher voltage. So here it was only charged to 0.7 volt, but now we charge it to minus 5 volts, because now we have minus 5 volt here and 0 volts on the other side. So after this has happened, the capacitor is charged to 5 volts. Now we switch the polarity again, and this means that this point here will instantly go from 0 to 10 volts because this one goes to 1 volt. We have 5 volt. Sorry, it goes to 5 volt. We have 5 volts across the capacitor. Means that this point goes up to 10 volts. And then again, the same thing happens. This point will start discharging through the resistor, and it would go down to 0 if there was not a diode, but there is a diode, and the diode will stop the process when you're the diode will stop the process because this point cannot go to 0 when this one is 5, because then this diode becomes conducting. Okay, so the diode will keep it at plus 5 volts or 4.3 volts if you take the diode drop into account. Okay, so this is the kind of response that you expect when you have an ideal diode with a capacitor in parallel. Yes. Okay, now if you do this with a real diode, it actually looks slightly different, and this is shown here. This is a simulation, but one that takes, of course, all the effects into account, and a real diode will do the same thing. So now we have this rectifier with a fast square wave input, but instead of this behavior that we expect from an ideal, we neither see the ideal diode nor the ideal diode with a bit of capacitance, but we see something else. So it looks kind of familiar. So this spike looks like what we expected. And here we understand why it goes a little bit below -5, but then it doesn't go back immediately, but it takes some time before it recovers. So we have this feature that there's a large current that flows for several nanoseconds, which is a long time in electronics, after switching from forward bias to reverse bias. And the effect that happens here is the removal of the minority carriers that were injected in forward bias. If you remember that when you have the diode in forward bias, the majority carriers are injected into the other side where they are then minority carriers, and they form a significant charge storage. So this charge storage must slowly be removed and causes this effect. And this is called a charge storage or a diffusion capacitance because it acts like a bit like a large capacitance. So this is here shown in a bit more detail. So when we have a diode current, a diode in forward bias, you have an excess of minority carriers on both sides. So here we show only the minority carriers. So you have some electrons on the p side and some holes on the n side, and it turns out that the total charge stored is proportional to the forward current. So the charge that you have stored like this is proportional to the exponential function of the voltage divided by the thermal voltage. So this charge versus voltage behavior is not a regular capacitor, obviously, because a regular capacitor would have charge equals capacitance times voltage. So this is not the case here. We have a voltage-dependent amount of charge that is stored. So you can either treat it as a voltage-dependent capacitance, and in this case, this would be yes. So this is a voltage capacitance, and so you can only write it as a capacitance meaningfully for small changes. So you can look at how much charge do we store in addition when we change the voltage by a little bit, and then the proportionality here is called the differential capacitance. It's not an ordinary capacitance. It's just a differential capacitance, and for this diffusion capacitance where you have this exponential behavior, you can take the derivative of this with respect to the voltage. You again get this exponential. So this capacitance, this differential diffusion capacitance, increases steeply with forward bias. Okay. However, when you instantly change the voltage, the charge is still there. Okay, so it does not disappear instantly, but it has to flow out again, and this is why you have this large storage time here, because the current is limited then by the resistor. It cannot disappear instantly. It has to flow through this resistor, and that limits the current that goes out. There's another capacitance, in fact, that is important, which is called the junction capacitance or depletion capacitance. So if you look at the depletion region, you see that we have fixed stationary charges in the depletion region, in the depleted volume. And if you increase the size of your depletion volume, that means you have more charge stored in this region, right? So the charge stored in the depletion region is a function of the width of the depleted volume and hence of the applied voltage. And we've seen that the width of the depleted region is proportional to the square root of the voltage across the junction, which is the difference of the built-in voltage and the externally applied voltage. Again, this is not a linear, not exactly a linear expression, but if you take the differential capacitance, so you get the derivative of the square root with respect to the voltage is then one divided by the square root. So for large voltages, this is then roughly 1 over the square root of the voltage. So these two effects act as capacitances. This is shown here as an example. So the diffusion capacitance is a steep function of the forward voltage, while the junction capacitance is only a square root function. It goes down for increasing reverse bias, but in the reverse direction it dominates, while in forward direction the diffusion capacitance dominates. So when you have applications where you switch a lot between forward and reverse bias, this diffusion capacitance becomes a problem for high frequency applications, while the junction capacitance dominates in a reverse bias. And it can also be very important in high frequency applications, for instance, in all integrated circuits and so on, in all semiconductor devices. But it can also be used. So you can use this diode as a voltage controlled capacitor. And the diode that is used in this way is called a varactor. This is an example here, an example circuit. Where we have an oscillator, so this coil, this inductor, and this diode. So we treat the diode as a voltage-controlled capacitor. So these two devices form our oscillator. This capacitor here doesn't really play a role. It's only meant to block the DC current here. So this capacitance is much higher than the capacitance here. It doesn't play a role in the circuit. So the LC is given by the capacitance of this diode and the inductance of this inductor. So we have to put this into reverse bias. We do that by this DC voltage here, and we add to this DC voltage some oscillator voltage and look at the frequency response of the circuit. And this is shown here. For different values of the DC voltage, which then change the capacitance of the circuit, and change capacitance here means that we see a different resonance. So the resonance frequency is 2 pi divided by square root of L times C, and the diode capacitance decreases with increasing voltage. So with 1 volt we have the largest capacitance, and then if you go to minus 10 volt, we get a smaller capacitance, and hence the resonance frequency goes up. And a device of this type is called a voltage-controlled oscillator. This is a building block that is used in many circuits where you need to control a frequency by applying an external voltage. There's another type of diodes that are used very often that don't have a PN junction. They are simply metal semiconductor contacts. These are actually historically the first diodes that were used. So when you have a metal with a work function that is higher than the energy that is needed to take an electron from the conduction band to vacuum, so that's called electron affinity, but that's not so important here. But so if you have a vacuum level here, and if you as a thought experiment take an electron here to the vacuum and then bring it back here, if you gain energy through that, then if you would bring the two pieces of material together, the electrons from this silicon would prefer to be in the metal, so they will eventually cross over into the metal conduction band. And this flow of electrons from the silicon into the metal then will cause a lack of charges in this region. So this region will charge up, which then creates a voltage barrier again, which eventually stops the electron flow. And this is shown here in terms of bands again. So the Fermi level will basically balance with the Fermi level in the metal, which is here in the middle of the conduction band, and the conduction band of the N silicon goes up here, forming this barrier. And the only current that you have left now is the diffusion current across the barrier, which again has this exponential behavior. Yes, so you have the diffusion, the diffusion of electrons from here to here, proportional to this barrier, and you have the opposite diffusion of in this direction, which is proportional to this barrier height. So if you apply no external voltage, of course the two currents must balance. So you know that these two factors are not independent, and we will call this the saturation current. And if you apply an external voltage that modifies the barrier, so we go from VD to some other voltage, then we know that the net current can be written like this. And we get again the Schottky-like IV curve for this Schottky diode. These are called Schottky diodes, and yes, these are in fact the earliest solid-state diodes that have been built. So maybe you've seen these historical pictures of radios where people needed to somehow make a scratch with a metal needle on a germanium crystal, to get their radio to work. In contrast to silicon diodes, normal silicon diodes, these have a small diode voltage, so much less than the 0.6 or 0.7 volts. It's only 0.3 volts. There's no minority carrier injection, so the electrons that hop over the barrier then become C electrons or valence electrons in the metal. So there's no minority carrier injection here. And no diffusion capacitance. So that's why these diodes are popular in high frequency applications. So the downside of this is that Schottky diodes have orders of magnitude higher leakage current than real PN diodes. So in most cases where the diffusion capacitance is not an issue and the diode drop, the higher diode drop is not an issue, you will still use the PN diode. But in these, in some applications where one of the two properties is more important than the leakage current, then Schottky diodes are used. Okay. Do we do this? Okay, let's briefly start with the light absorption in PN junctions. So when no, actually, let's keep this for next time. We'll stop here and continue next time. Okay. Okay. Thank you. So the next week the lecture will be only on Zoom. Okay. So nobody should be here. But then the exercise will probably, so the practical exercise will probably still be in this room, but not the lecture. Okay. Okay.